Good morning. These steps are still as hard to walk down as they were 10 years ago when I did my thesis presentation here. I presented at the second one of these conferences, so thanks for having me back. I guess I didn't do too terrible on the job that time around. I'm Satchel. I'm an engineer at ABB here in the US. My title has a lot of other adjectives, but we'll just stick with engineer. And ABB is a global giant company, but we deliver in the US electric propulsion systems and hybrid propulsion systems for Jones Act vessels, primarily tugs and ferries, two of which we have, or three of which we have in service, and a lot more in the pipeline. So today I'll be trying to share lessons learned that are applicable to naval architects and marine engineers from the projects we have already delivered. So I'm going to talk about route profiles and what those are and how to develop one. Equipment ratings and how that differs for electric propulsion systems from typical diesel vessels, some guidelines on how to allocate space for an electric propulsion power plant in the early phase of design, and then the lessons we've learned from different types of shore charging projects. But first, I'd like to poll the crowd. What are the major risks, major design risks in any type of ship design? I'm going to take 4 answers from students only. Everybody ready? Yes. Cost. Great. That's one. Yes.
Meeting the owner's requirements.
Specifically, which ones?
Cost.
You love the same answer twice. Yes. Weight. Great one. Yes. Speed. Nice. We're going to take 5 because I didn't get any first-year students. Somebody? Yes.
Feasibility.
In terms of?
It can all work together.
Yeah, great, perfect. So I came up with some too. You came up with some that I didn't, but we got weight growth, lack of space, so let's call that feasibility. Stability, speed, and power meeting the functional requirements. And really, if you look at this, slightly small text, but if you look at this list, really weight growth and lack of space kind of lead to those stability and speed and power problems that you might have meeting owner's requirements later on. So I'm going to try to give you some rules of thumb to focus on how you can address weight and lack of space early on in the design. So this all starts with a route profile. And what is a route profile? It's basically just a calculation of how much energy the vessel needs to do its job. For a ferry, that means how much energy it takes to get from point A to point B and carry the passengers and cargo that you get paid to do. For a traditional diesel vessel, this would just be design speed and range before refueling. For a hybrid or all-electric vessel, you need to include the cycle energy, so specifically that one trip between charge time, how many trips per year, and then how many years of operation you're designing for battery replacement. So looking at an actual example, this is for the Islesboro replacement project that we're working on right now. The traditional vessel had an operating speed of around 13 knots and 1,500 nautical mile range, meaning it has to refuel every 3 to 4 weeks. The hybrid electric solution, which is all electric for the crossing, and actually we only charge on one end because there's more power available on the mainland and not on the island. That's a 2.8 mile crossing, so approximately a 5.5 to 6 nautical mile trip with in between charging. And you'll see that I've got it on the bottom of the slide here. That's almost a 250 times difference in range, right? Taking a 6-mile vessel and going to 1,500 miles, which basically means you need to be 250 times better at calculating the speed and power of the vessel. And then I can see that the older students know that that's not possible, right? We struggle with 5% precision, we struggle with 5 to 10% precision in speed and power calculations as it is. So you have to be really cautious about how you apply the margin and calculate these route profiles to make sure the vessel is going to, get to the other side. One of the ways, or really the way to do that is to really look in detail, very specifically at how long the route is, how much time is spent maneuvering between docking, how long it takes to connect the charger, and literally down to seconds to calculate this. So you'll end up with a table that looks like this. for each phase of the voyage. This is a double-ended ferry, so we have propulsion power from both ends. And you'll see the durations of each stage of the voyage. So you're looking at the speed and power we talked about, current, and the impacts of current on the vessel. For those of you who are racing sailors, you know that sailing in negative current is never something you want to do because it's a double negative. You're going slower because of the current, and you spend more time because the current is literally moving you backwards. Current's really crucial to include on a ferry route. Weather and consistent wind direction and the negative resistance impacts. The duration, sometimes there are trips where for navigational reasons, the vessel has to spend longer than its average speed on that route. And then loading conditions. If you're carrying a lot of cargo on one route and deadheading back with a lighter vessel, that's going to change the resistance. And then finally, hotel loads. And I'm going to get into this more later, but hotel loads are really the bane of my existence. They just always go up and they're always present, right? If you slow the vessel down, the route takes longer and now you need to capture more hotel load energy on the crossing. So it's really a pain. So once you have a route profile, let's talk about equipment ratings. Obviously, propulsion is the number one equipment that we need to provide. And electric motors are fairly different than a diesel engine in terms of how they're rated, right? The electric motor can produce full torque across the entire speed range, which makes matching it with the propeller a little bit easier. Also, the torque of an electric motor is literally limited by the diameter, the frame size of the motor. As you can see here, this is the actual motor from the Islesboro replacement project, and it's got about a 1 meter diameter to be able to produce the torque. Now that's a lot more diameter than the Artemis vessels, right? So we're running at a much lower RPM. My advice to you would be select a motor with some margin on torque, and you can, over the course of the design, match the exact power and RPM operating point as long as you have enough torque margin. Onto the batteries. Batteries are sized by the route profile, the maximum C rate, which is how fast you need to charge or discharge the battery, so the maximum power that you need, and then the lifetime. And so the lifetime is calculated typically by ABB or another integrator or the battery vendor because it's pretty proprietary. But you can see, the green line here, or the blue line, is the calculated state of health. So if you want a 10-year life, this is how much energy you can provide on each cycle. And if you build this vessel and you put it into service and somebody says, oh, we need to go a little faster, and you use more power, the battery will not last 10 years, right? And so, but if you use less, the batteries will last longer. My advice here is that at some point in the design, you need to freeze the route profile and the battery size, because otherwise you will be chasing the exact battery life down to the day you deliver the vessel and into operation. And so at some point you need to just say, we're going with 10 megawatt hours, and if the life is slightly shorter, we will adapt operationally. All right, I put I think it's a pretty good meme up here for this one. This is not a joke, right? Electrical equipment literally depends on cooling. And this comes back to my hotel load points. There's two lessons here. First, one is account for water cooling and air cooling in the design early on, right? Every piece of equipment that we're providing is going to need it. The second is about how this equipment adds up in hotel loads. And in general, if you're using a parent vessel, which is very risky, and there's a great article from Professor Collette at University of Michigan online about why parent vessel design is risky. But if you're doing it specifically, the electric load analysis is extremely risky to use as a parent input, because the hybrid or all electric vessel is going to have a higher electrical load. We've got cooling pumps for all these systems, often 2 circuits, cooling fans for pretty much everything. There's anti-condensation heaters in most electrical equipment, transformers, propulsion motors, the multi-drive lineups that we provide to prevent condensation when the equipment cools down. There's UPSs for control power for all of the control electronics. And then you need HVAC for battery rooms and the multi-drive switchboard rooms to prevent condensation also. So yeah, really we typically see for a similar size vessel, hotel loads in the 50% to 100% higher than a diesel vessel. Okay, moving on to space allocation. This is maybe where I can be the most helpful in these future preliminary designs. What is the hybrid system actually consist of? We have the propulsion motor and the batteries that I showed you, and then you need the electrical backbone, which is a multi-drive lineup on a large-scale commercial vessel or ferry or tugboat. ABB, we call this onboard DC grid. But how do you define this? For the purposes of this presentation, I'm going to call a multi-drive lineup a group of converters, either AC to DC or DC to AC, that are built into cabinets and end up looking like a switchboard. And I haven't included any pictures because it's just a wall of white cabinets. It's the most boring, but it's the most important piece of the system. And you can see on the right here, the section view. For an ABB product, the cabinets, the multi-drive lineup is going to look like that. 2 meters tall, 600 millimeters wide with the space allocation. And that's just going to be a line of those. And I'm going to show you on the next slide how to figure out how big that line needs to be. So I took the 5 projects that we worked on most recently and tried to make some metrics here based on size. And these presentations will be available after, so you don't have to try to read the small numbers. But I'm not a data scientist, and I only have 5 samples. And I'm sure that there's somebody who can tell me the trend lines aren't particularly, but I think they're good enough for preliminary design. All right, so we're looking at lineups from 12 meters to 70 meters long. That's for installed propulsion power here on the x-axis of around 1 to 12 megawatts. So if you're designing a vessel in that size range, feel free to use this data early on to look at how much space and how much weight you're going to have. I will say the distinction, I'm actually surprised by how consistent this came out. And the distinction between data points that are above the line and below the line is based on what type of shore charging solution they're using. And we're going to talk about shore charging more in a second. Okay, and then the last space allocation topic here, control cabinets. I don't know if anybody here is into biking or other equipment related sports, but there's a typical saying that is the right number of bikes to have is N+1, where N is the number you currently have. And you all can solve for the limit of where that goes to. That's kind of how we are with control cabinets. These are the CPU, right, or brain, or more specifically, the PLC that is used to control the automation system behind the electric propulsion system. And basically, there's a computer in here, and then there's input-output cards that connect to the cables that connect to all the sensors throughout the vessel. So you're going to need a lot of these, right? The vessel we're using as the case here has 2 motors and 2 engines. So that's 4 cabinets there, plus these other 4 for the control system and the remote diagnostic system. So you're looking at at least 9 of these, right? So just start by putting them in your design. It'll make your and my life a lot easier later on. You can really never have too many control cabinets. Okay, final topic for today. And I'm glad to see I've made up some time, which probably means I'm speaking too fast. But shore charging. This is one where we've learned some pretty maybe funny lessons. But I'll just start with the overview of the 2 types of shore charging architecture. And really, shore charging is what makes hybrid or all-electric vessels possible. It's what makes these vessels cheaper to operate, typically. It's what makes them better for the environment. And it's pretty cool to see a robot, manipulating and plugging in a plug onto one of these vessels. Also, I will point out there is a movement to put in shore charging systems in offshore wind farms to use the power that comes directly from the turbines, which maybe isn't onshore, but it does allow you to operate an electric vessel in the wind farm, wind construction space, which is pretty exciting. So starting with AC charging, right, alternating current, you have mains power, as they say in the UK. That's for Artemis here. Then you go to a utility transformer, and then a contactor and breaker combination. Breaker providing protection of the equipment, and the contactor switching the line. We'll talk about why that's important. Then you typically have an isolation transformer, either on the shore or on the vessel for galvanic isolation. And then the charging system, which can just be cables handled manually, or for a ferry that's making 15 to 20, 30 connections a day, an automated robotic connection system. And then you have a plug or a socket on a vessel, another contactor and breaker on the vessel to prevent backfeeding power and faults in that direction. And then the AC to DC converter, the onboard DC grid, and the batteries that you're charging. For DC, you have the same mains power and utility transformer, but then you have the converter on the shore side, the breaker, and I'm putting breaker in quotes because DC uses a different technology, and we'll talk about that in a bit. The same kind of charging system. In fact, most of them are designed to do either AC or DC, and you can select it when you buy it. But then on the vessel, you just have the socket, and the power goes straight to the DC grid and batteries. So looking at the difference between these two systems, in AC, you have less landside equipment. And if you use a medium voltage, 6 kV up to 20 kV, you can provide a higher charge rate, sometimes as high as 15 megawatts, or we're now seeing larger systems. On DC, shore charging, you have less equipment on the vessel. You require less transformers, which are in the current global supply chain a very long lead time item. And it's feasible up to around 6 megawatts of charging power. We're working to push that higher. And then finally, you have support for landside batteries, which is important for a lot of ferry operators who buy their power in the wholesale market and have to pay a higher rate when they when they spike and you pull really high power for a very short period of time. So you can buffer that with batteries or have your own landside solar system to recharge. Okay, last section here, some lessons learned from shore charging installations. And I put the title here, who is responsible, because that's maybe the first lesson. Shore charging is a physical integration, an electrical integration, and a controls integration between the vessel and land. And I'm going to make the argument here that the naval architect should be responsible, because you just can't trust those landside engineers. So the first lesson we learned on a project that's being installed currently is the transformer secondary grounding. And you're going to have to ask Prof. Martin more questions about this in class, because I'm, remember, a naval architect working for an electrical company. But utilities like to provide that utility transformer, but they require that the secondary be solidly grounded. And solid grounded secondaries really does not work for a shore connection for two reasons. One is the system is not, the charging arms are not designed for solidly grounded because they don't do it that way in Europe. And the second is solidly grounded makes it really hard to galvanically isolate the vessel from the shore, which is crucial and the topic of a whole other presentation. So we have a project where the transformer is solidly grounded and already installed, and we're working on resolving that. The second one is anytime you have a shore charging connection, you need to make the line or the mains, whatever you want to call it, dead before you plug it in, right? This is like when you plug something into an outlet, you don't have to tool on before you plug it in, because it will arc. And an arc at 480 volts is dangerous. An arc at 12 kV is explosive. So making an automated system, making a power connection is also not a very common thing for shoreside electrical engineers. And so they aren't used to that. And we actually have a project where things were installed that didn't include the contactor and the PLC necessary to switch the line at every connection. And we've had to put in a whole nother switchboard on land. And then finally, for DC charging systems, the shore electronics that convert to DC provide power to the ship. And in the event of a fault on the ship, these systems also need to protect the ship, right? They need to be able to prevent the fault on the ship from causing a fire, which requires that breaker, which in DC is typically an IGBT-based static switch component, At ABB, we call this product an input circuit, but it's made by a few manufacturers worldwide and very specialized, and definitely something shoreside electrical engineers are not familiar with. So for those three reasons and lessons learned, I'm recommending the naval architects be responsible for the overall integration and ensure that the electrical contractors are on the right path. So that's pretty much all I've got today, except for one more piece of advice, which has come up this morning already. In the words of the ex-governor of Rhode Island, who ran on this platform for president in 2015, please just use metric. All right, thank you.